Behold this infinite mathematical universe. A dizzying cascade of fractals. Arrays of complex patterns filled with both satisfying self-similarity and surprising novel features.
All of the structure and the patterns that you see there really do exist for a reason. There is some sort of innate mathematical cause behind all of the phenomenon that you see.
This is the Mandelbrot set. These trippy images represent a form of modern algorithmic exploration, one made possible by computers. A handful of mathematicians have devoted their lives to uncovering this set's secrets.
It plays this very central role in our understanding of much, much more complicated systems. It is step number one.
And we may be on the verge of finally understanding it. So what exactly is the Mandelbrot set? And how does it work? The Mandelbrot set is a perfect example of how a simple rule can produce incredible complexity. At its core, the set is generated by iterating a quadratic equation, a simple formula whose highest exponent is 2. To iterate a quadratic equation, choose a value for the variable. Plug it into the function, then take the output and feed it back in again and again. The study of how recursive functions like these change over time is central to a field of math called complex dynamical systems.
This subject came about with the goal of understanding the real world. What are the mathematics that underlie the physical world that we see? Most important early example would have been the solar system.
So dynamical systems that you have some space where you have some rule that's deciding as time moves on how that space evolves and how things move and change.
In the early 20th century, mathematicians Pierre Fatou and Gaston Julia set the stage for the discovery of the Mandelbrot set with their exploration of dynamical systems. To investigate these dynamical systems, mathematicians study intricate shapes today known as Julia sets. Julia sets are produced by iterating a function of complex numbers. A complex number is defined as the sum of two components, a real part and an imaginary part. Each complex number can be visualized as a point in a 2D plane. The real part is a number found on the number line. The imaginary part is a multiple of the square root of -1, which mathematicians write as I. Despite the name, imaginary numbers play a vital role in solving real-world problems. To construct a Julia set, start with the simple quadratic equation. f of z equals z squared plus c. Choose a value for c, like -1 for example. Then consider what happens when you iterate this equation for every possible starting value.
You repeatedly apply the function to this sequence of numbers that you're generating, and you ask whether or not that sequence is going off to infinity or whether it stays bounded.
For some initial values, your equation speeds off to infinity when iterated like this. These values are not in a Julia set. When you start iterating from other initial values, you might instead get a sequence of outputs that stay bounded.
When something comes back to itself, often we call that recurrent behavior, and that's where the complexity arises.
The boundary between points that stay bounded and those that don't is a Julia set. You can fill it in by including all the bounded values. Different quadratic equations generate a wide range of filled Julia sets, from basic blobs to intricate twisting tendrils. Filled Julia sets can be divided into two categories. Sets where you can draw a line from one point to any other without lifting your pen are connected. Sets where points look like scattered pieces of dust are disconnected. The first rough plot of the Mandelbrot set appeared in a 1978 paper by the mathematicians Robert Brooks and J. Peter Metelsky. Soon after, Benoit Mandelbrot, a researcher at IBM who had access to more computing power, also discovered the set. This led to further explorations. These early computer graphics were crude, but the patterns revealed the presence of something far more complex.
Even with fuzzy, poorly made pictures in the 80s, they were able to really glean a lot of interesting insight into what's going on.
Mandelbrot went on to popularize his now eponymous set to the world and became known as the father of fractals. Today, mathematicians can use computers to explore the Mandelbrot set in far greater detail.
As soon as you have images, just opens up this whole world.
The Mandelbrot set is drawn in the complex plane. It's constructed by iterating the same quadratic equations used to produce Julia sets. But here, things are flipped around. Instead of iterating all values of z for a fixed value of c, we fix the starting value of the iteration at 0 and vary c. Values of c, where iterations of z squared plus c stay bounded, are inside the Mandelbrot set, while those that go to infinity are not. Here, we can select points inside the Mandelbrot set to reveal their corresponding filled Julia sets. The Mandelbrot set acts like an atlas, cataloging the different kinds of Julia sets. Values of c inside the Mandelbrot set are associated with connected Julia sets, while values outside the set correspond with disconnected dust. The Mandelbrot set has many intriguing features, but its biggest mysteries lie in its complex fractal boundary. Zooming in to different boundary regions reveals some astounding features. A valley of seahorses, parades of elephants, and miniature versions of the set itself.
So we can sort of keep finding nests, a sequence of smaller and smaller Mandelbrot sets, all one inside of the next.
Here at the boundary, mathematicians are probing for answers.
As you look at it, it sort of seems like one blob, but if you really ask, like, is it all connected? Or maybe if I zoom in far enough, there's some separating piece.
This question is central to a 40-year-old problem called the Mandelbrot Locally Connected conjecture, or MLC. If the set is locally connected, that means that no matter what point you choose to examine, or how far you zoom in, the area will always look like one nice connected section. For example, if we closely examine a circle, we can see that it's locally connected at every point. But take a fine-toothed comb and zoom in. While the comb is one connected shape, at close range, it can look disconnected. If mathematicians can prove that MLC is true, then a complete understanding of the Mandelbrot set would be within reach.
This local connectivity question, if we can answer it, if it can be solved, this will give us almost complete control and understanding of what's going on. The hope is that once we completely understand quadratic polynomials, we can go on to looking at more complicated dynamical systems and be able to describe them more and more.
But a full understanding of the Mandelbrot set wouldn't put an end to our collective fascination with this famous fractal.
Hard to imagine that it wouldn't be interesting to people even if we fully understood it, because it is so complicated and so rich and so beautiful.